Why do these two sets have an equal number of elements? Well, you count, right? So 1, 2, 3, 1, 2, 3. 3 is equal to 3, so these two sets have the same size. Now I know I sound like I'm trolling, but I'm getting somewhere here. The problem with this definition is that you can't apply it to infinite sets. You can't count infinite sets, right? What if we change the definition to this? Two sets have the same cardinality if there exists a bijection between them. And the good thing about this definition is that it subsumes the previous definition. And by that I mean they agree in all answers. Let's take that example, and once again, these two sets have the same cardinality because you can biject them. And these two sets do not have the same cardinality because there does not exist a bijection between them. And this definition extends to infinite sets. You can definitely talk about bijections between infinite sets. Let's take a very simple example, n and 2n. These two have a very clear bijection, therefore they have the same cardinality, which is kind of counterintuitive, right? Because one is a proper subset of the other. This can only happen with infinite sets. Another important result is the fact that n has the same cardinality as q, which is even more counterintuitive. Now why stop at equality? Let's define something for less than equal to. Again, for finite sets, this is simple. 3 is less than equal to 7, so the size of this set is less than equal to the size of that set. For infinite sets, let's try this definition. The size of a set is less than equal to the other set if there exists an injection from that set to the other set. Again, this subsumes the finite definition. The size of A is less than equal to the size of B because there is an injection between them, and the size of C is not less than equal to the size of D because there does not exist an injection between them. And this definition extends to infinite sets. Now with all these definitions, you can sort of order all the sets. That's greater than that, that's greater than that, and so on. And there are so many famous results. One example is the size of R is equal to the size of the power set of n. The size of R is also equal to the size of all infinite tuples of 0 and 1. And a really interesting one is called Cantor's theorem, which states that the size of the power set of a set is strictly greater than the size of the set itself, which has a surprisingly short proof despite how profound it is. Also, you might disagree with this being our definition for the size of sets, which is fine, but I am not aware of any other more reasonable definition for size of sets. And this definition is ubiquitous throughout math. One end tangent here. I have skipped a lot of results in this reel because of time constraints. If you guys are open to more long form content, do let me know in the comments, especially the platform. I'm thinking of YouTube and putting the clips here, but yeah, let me know what you guys think.